All right, with the last video, we were just talking about the apparent magnitude scale, and what we're about to do. What I'm about to talk about is this. Relating the logarithmic scale to absolute magnitude. I'm sorry, relating totally messed it up. Relating the apparent luminosity to the magnitude scale, to the apparent magnitude scale. And so what's important about this, and I think I was kind of hinting at this at the end of the last video, is that that the magnitude scale that Hipparchus came up with is actually a logarithmic scale. So the basic idea here, as it says here, is if you changed, let's say you went from a 0th magnitude star to a 5th magnitude star, then that actually changes the apparent brightness by 100. So every change in 5 magnitudes on this magnitude scale, which is really a reflection, the magnitude scale is pretty much a reflection of what our eyes do. Every change in 5 magnitudes is a change in the apparent luminosity, or the brightness, if you will, by 100. Okay, so don't keep this scale in mind. This is actually an interesting thing. This, remember, the humans can see without anything, just their eyes, to about a 6th magnitude, and anything more than that, you need either binoculars or telescopes. And like a pretty good amateur telescope. So this is like a telescope that is in the, let's say, $3,000 to $4,000 range. If you were going to buy an amateur telescope that was about 10 inches is the what they call the, well, not actually 10 inch. You could think, about $3,000 or so. So that you could see to a 14th magnitude. You could see, for example, I used to have one that was like a 12-inch telescope, and I could see, for example, the Ring Nebula, which is a famous nebula in Lyra, which I think is about a 12th magnitude object. So if you now you get up to the professional level, then you're talking about a meter. So that, the opening is at least a meter, if not a lot more, right? So there's much bigger telescopes out there. The Hubble Space Telescope is actually not that particularly. It's a large telescope. All right, so I just paused the video for the recording here for just a second, because I actually had to look up what the aperture of the Hubble Space Telescope is, and it turns out it's about 2.4 meters. So that's the size of the primary mirror inside of it. The Keck telescope, I think, is 10 meters, if I'm not mistaken. Let me look that up. Yeah, so I just looked up the Keck telescope. It's actually they're twin telescopes. They're on they're in Hawaii. They're very famous telescopes that we use all the time in astronomy, and they're 10 meters, right? So they're much larger than the Hubble Space Telescope. But of course, the Hubble Space Telescope is above the atmosphere and can get some incredible images of the heavens. All right, let's see. Well, let's change the factor. So don't forget the idea that the brightness, the larger the magnitude, the larger the number. Like, for example, here it tells us like the Hubble Space Telescope and the Keck can get up to a magnitude of 30. So that's a very, very dim object. Very, very dim. All right, so anyhow, let's move on. Luminosity and apparent brightness. If we know a star's magnitude, so this is really what we're building towards. If we know the apparent magnitude, of course you can measure that, and its distance from us. So you look at a star, you measure its apparent magnitude. Now, of course, we just talked about distances to the closest stars, right? The closest stars, like if you extended a radius out about 200 parsecs, I mean, you're picking up millions of stars in that situation, and so we can measure directly the distances to those stars, and of course the apparent magnitude, and then what we can do is we can calculate their absolute luminosity. That is, it's as though you're looking at that star. You can tell like what the actual power coming right off the surface of the star is. In other words, I always explain this in the following way. If you know that you have a 100-watt light bulb, so you know that ahead of time, it's stamped, it's factory stamped on the light bulb itself, and it was nighttime, and you were somewhere on campus, and somebody turned on that light bulb, and you'd have to have equipment to be able to do this. You'd have to have a photometer to actually measure, how much energy you get. So let's say you do have the photometer, and there's the light source. And if you already know that it's a 100-watt light bulb and it's somewhere on campus, by measuring the amount of flux that you get, remember that's the amount of power per unit area that you get, you can use the inverse square law in reverse to figure out how far away it is. Right? So that's the thing that we really want to get to. So of course, we can measure the apparent magnitude, but the problem with this idea is, how do you get the luminosity, the absolute luminosity? Like, how do you know how bright that star would be if it turns out that in astronomy, we use a standard of 10 parsecs away. All right, so we'll get to that in just a little bit. All right, so here's another piece of information that we can get from stars. Like if you look up in the night sky in the winter time, this is a very prominent constellation, the Orion. There's the belt of Orion. Orion's nebula is just below, and that's actually a naked eye object, by the way. This is a place where stars are being born. That's not really what we're talking about. Notice in the upper left-hand side, that's the star Betelgeuse, or Betelgeuse, depending on how you want to pronounce it. And the lower right-hand side is a very bright star. This one is a whitish star. It's kind of white to maybe a tinge of blue. That's the star Rigel. It's an extremely bright star. And this one right here is called Bellatrix, by the way. Anyhow, how do we know the temperature of a star, right? Now we learned already. We know about Wien's law, right? And from Wien's law, you would have to figure out what the maximum wavelength is, right? And then you use Wien's law, which we used in chapter, I think it was chapter 3 chapter 3, and we used it in chapter 4 as well. You could tell how hot the star is. Now that's fine. That's certainly a great way to do it. But now in reality, okay, in everyday, you're a run-of-the-mill astronomer, and you have so this is the way it works. If you get access to a telescope, and it's usually not just you, it's usually a whole team of people, and so your role is just generally a pretty minor. Well, it can be pretty minor. It seems that way sometimes. a pretty minor thing where you are in charge of one little aspect of the observation. But see, so generally the telescopes will grant a group of astronomers a certain amount of time, and so you're just limited. Let's say you get let's get really optimistic. You get a whole week of observation time with a really large telescope. Not like the Keck telescope. That's pretty that's hard to get. But let's say a moderate, let's say a 4-meter telescope or something like that. Anyhow, if you have a week, suppose it's raining part of that week, right? Which does happen, certainly. And then, what can you do? Suppose you were tasked with looking at, a certain group of stars in some portion of the sky, and you wanted to know what the temperatures of those stars were. It would take a long time to, and this is really my point, it takes a long time to figure out exactly where that peak is, where the high. So because you have to, you can't just look at the star in one particular color and find where that peak is. Okay, it's more. I mean, we present it initially like it's a really trivial thing, but it's not. I mean, in practice it takes some time to actually find that peak. Well, there's a way around that, all right, and this way around that has been used for a long time in astronomy. What we generally do is we use what's called the B filter and the V filter. There's other filters as well, but those are the primary ones that often get used. The B filter looks at primarily like ultraviolet light, or I'm sorry, it filters all the light except for kind of part of the blue part of the spectrum all the way to the into the ultraviolet. And then the V filter that stands for visible. Will just give us the visible part of the spectrum. And see, without figuring out what this peak is, again, this takes a lot of observation time, and sometimes you don't have that amount of time, especially if you're looking at a whole bunch of stars. All you have to do is look, using a filter, just look at the star in, let's say in the B and in the V, and usually we subtract those. But anyhow, you get the idea. You can do this with any particular star, and because the stars are essentially perfect black bodies, and we know what these curves look like. If you get 2 points on that curve, or 2 parts of the curve, you can mathematically figure out where this peak is. That's, in practice, the way we can measure the temperature of the star. I mean, there are certain times when a particular star is of extreme interest, and we want to know exactly where this peak is. We will use this technique, but then we'll go looking for it. And of course, you would do this. So the technique of using the filters to figure out what the curve would look like, and then ultimately, it might not be your team, it might be some other team of astronomers, might be able to have time to go and look at that particular peak. But see, again, you're talking about, if you just included the stars within our galaxy, which we've never looked at every single star in our galaxy, there's over 200 billion stars in just our galaxy. So again, it's only of stars that are of particular interest that you want to do both, right? So usually it's just using the 2 different filters, extrapolating to where the peak is, because again, we know what the curve is, right? These 2, you can tell the curve is going to be over here, right? Well into in the red region. These 2, it's pretty much invisible, right? I'm talking about this middle